Hi everyone, welcome to another installment here of the World Simulation Engine. Basically I have a bunch of particles here rendering in the GPU. Basically what I did is short-circuited the calculations and output values at specific times of the shader invocation, and which caused an update to the buffer. So it got a matrix of data. I believe the width of the data is 32, and times a fixed length of data, which would have been times a fixed length of data lines, which was set to about 1024. So what it does is it goes through all the objects, gets all the x, y, velocities, etc. that's currently on the object, and then sends them to the GPU for number crunching. And then GPU basically number crunches the values and sends it back, and then I just reconcile the numbers afterwards. So this simulation currently is running entirely on the GPU. Right here I have some JavaScript that gets compiled using GPU.JS. It's a really nice library system. It gets compiled into shader code, which means I have to abide by certain semantics in order for that to work properly. So as you can see there, that thread y limits it so that it doesn't execute on the first line, which is the global line. It has all the global data regarding the world, and everything past line 1 is all object data. So basically, as it goes through the code, processing and number crunching, it short circuits and exits out. And the tricky part was that I had to only return a number. I can't return more than one data element, only one. So as shaders execute, they process input data and then they output just one piece of data or color. But in this case, I believe it outputs floats. GPU.JS outputs floats for this case. And so what I could do is actually have multiple buffers and have two input buffers, one for x velocity and one for y velocity, and then compute gravitational forces on those, or so on and so forth, or whatever the case might be. And then I can just send that to the GPU and have it processed. And code executes downwards until it comes across one of those out index entries. And so when you get to out index 0 or out index 1, so on and so forth, which represents the thread x horizontal location, what it does is it returns the value at that particular point. So it sort of short circuits the code execution at a particular point in time, returning only that particular value. And this code here converts the JavaScript function string into something I can run on the CPU instead of the GPU. And I basically have a Boolean variable that lets me toggle between the two. So right now I have used GPU, and so it sets up data to be sent to it. However, in this case, I can also use the non-GPU processor, which is just CPU. I could have just called it the CPU processor, I guess. In any case, again, this is just proof of concept, so I'm just kind of developing quickly here. And on the top here, you can see it actually will fill that buffer with data, and then later on chooses which one to execute, whether it's the GPU or CPU, and then it reconciles that data in the loop below it. And here we have it. So basically we have 1004 particles all being rendered on the GPU at about 11 frames per second. It is somewhat consistent because it is running on the GPU on a fixed buffer. However, I still have to compile the values of all the objects together into the buffer in order to send it, and that does take a bit of time. But that is currently executing on the GPU entirely, the physics at least, and other grid calculations and so on and so forth. And the collisions are still handled by the CPU. That's a little bit more complicated because it involves the grid as well, and it's a lot more data than I can send to the CPU. Sending too much data and buffers to the CPU just incurs a lot of overhead and transfers as well. So I'm not certain if that's a good idea or not just yet, but I'm still thinking there's ways to optimize it even now. Just sending multiple buffer streams to the shader instead and have them calculate the different values on output. So we'll see how that goes. And here's just a few more particles. You can see there's a consistency of about 22, 23 frames per second with only a small number of objects, because it has to send the entire 1024 by 32 buffer on every physics loop in order to calculate it. It's actually quite impressive that I can send that much data back and forth, calculate the physics, and still maintain over 20 frames per second, so that's actually pretty good. So here I have Chrome on the right and Firefox on the left, and you can see already the frame per second that's there. We have 14, 15 frames per second in Chrome, and Firefox has 23. 22, jumping back and forth there. It seems to me that Firefox is the best optimized for at least WebGL in this particular sense, but the CPU processor for the physics and other calculations also runs extremely fast in Firefox. So right now, Firefox is the fastest for calculating my simulations. So I have been just sticking with Firefox for really benchmarking the whole system. And here I can switch it back to the CPU. And so here we have Firefox running the simulation in the CPU. And because it's not outputting all the buffers all at once on every loop, it's much faster with a small number of items. And I also have in here a grid system that is dynamic. Again, as I mentioned in the previous videos, there's no fixed grid. Objects just grow to infinity in either direction. The grid will keep growing too, but there is a min-max x and min-max y on this virtual Cartesian plane. And by default, I have it set to 1,000 cells in either direction. And the grid is used for collisions. And if an object moves into a cell and there's another object there, it steps back and does not go into that cell. So it's sort of capped from going into that cell. And of course, the collision itself should already invoke equations for elastic collisions that cause it to bounce. The particles are trying not to occupy the same space as other particles. You can see them bouncing around there. But if an object does get bounced far enough out of the grid zone, then it will eventually get deleted. So this is running on the CPU now at the moment, of course. I had run this, I believe, in Firefox for up to almost an object count of 2,000 at one point. It does get quite slow, but it still maintains an adequate frame rate even at 2,000, so that's actually quite impressive. I managed to optimize the grid system and a few other JavaScript routines to speed this up, and I think there's still a bit more I can do to make this much faster. At least now I'm able to get at over 1,000 at pretty much 40 frames per second, or almost 40 frames per second at 1,017 particles. And again, these particles have real-time physics being calculated on them for velocity and gravitational force of the invisible world there that you can't see. It's for the center. Well, thanks everyone for joining me on this journey, this development journey of discovery and different ways of creating particle simulations. And please subscribe. I look forward to having more people engaging in comments and asking questions. It helps me learn, as well as anyone else who might be asking the questions. I'm always looking for ways to improve. Perhaps other people have other ideas as well that I haven't considered, but I know you haven't really seen the code, so it's hard to say. The code isn't going to be released at any time soon. At some point it would be interesting to see other people's simulations, but I have a lot of work to do before I even get to that point. Perhaps at some point in the future, when I have it more stabilized, I can start allowing people to do some stuff with it. I want to create some animation tools and some other utilities on the UI as well to help work with the worlds. It'll be integrated with an HTML5 web page, so I'll probably just use those actual controls on the page and then have the simulation run in the center, at least for now. And yeah, so it'll be interesting to see if any kind of game can be made from this. And thanks again for watching, and I'll see you next time. Bye.